In this video, I will be discussing the Bloch sphere in quantum computing. The Bloch sphere is a mathematical representation used for quantum computing that can visualize the state of a qubit. Qubits are a fundamental unit within quantum computing. In perspective, a classical bit can either be a 0 or 1, whereas a qubit can either be 0 or 1, but also a combination of both. In mathematical terms, we represent this as phi equals alpha state 0 plus the beta state 1. The qubit phi is a superposition of the basis states 1 and 0. Alpha and beta are also complex numbers with the property of the absolute value of alpha squared plus the absolute value of beta squared equal to 1. Alpha and beta are also the amplitudes of our basis states. Given that alpha and beta are real numbers, we can view the quantum bit in a two-dimensional Euclidean space. From here, we know that the amplitudes are complex numbers with both real and imaginary parts. This gives us a representation with four real numbers, having alpha equals the real part of alpha plus the imaginary part of alpha, beta equal to the real part of beta plus the imaginary part of beta. This can also be visualized on the right side here with our diagram. These complex amplitudes can be represented in an exponential form, giving us R alpha times e to the power I psi alpha base state 0 plus R beta times e to the power I psi beta base state 1. This is then times by e to the power of negative I psi alpha, resulting in a new rule that can be expressed phi in terms of three real numbers, where we have psi is equal to R alpha base state 0 plus R beta e to the power of I psi beta minus I psi alpha to the base state 1. This doesn't change any of the physical properties of the qubit. It only changes the argument of the complex amplitudes. The absolute values are unchanged, and from a physical point of view, it is completely unchanged. Because we are following Pythagoras' equation of R alpha squared plus R beta squared is equal to 1, we know that the absolute values of alpha and beta can be represented as an element of 0 and 1. The square of each absolute value of the amplitudes is the probability to measure each qubit in the corresponding basis state. Because we know the qubit will be in one of the basis states when measured, the sum of the probabilities must be 1, supporting this equation by Pythagoras. From here, we gather that the dependence of R alpha and R beta can be represented using the unit circle. So using the first quadrant, we have something like this shown on the right side, where the angle highlighted can be defined as pi on 2 for simplifying things later on when we're looking at the Bloch sphere. We can use this angle to express our absolute values, giving us the following. R alpha is equal to cos theta on 2, and R beta is equal to sine theta on 2, where theta is an element of either 0 to pi, which could also be 0 to 180 degrees. Given these terms, we can now express phi in terms of two real parameters, giving us phi is equal to cos theta on 2, state 0, plus sine theta on 2 times e to the I psi base state 1, where psi is equal to the difference between psi beta minus sine alpha, and the angle of psi is an element of either 0 to 2 pi, but not including 2 pi because that is basically 0. So theta can be calculated using the inverse trigonometric functions, giving us the following expressions. Theta equals 2 cos to the power negative 1 r alpha, and theta also equals 2 sine to the negative 1 r beta, where theta is an element between 0 and pi. Now we can use theta, the polar angle, and psi, the azimuthal angle, to determine a location on the unit sphere. Given our two angles, theta and psi, phi can be assigned a certain point on the sphere in relation to these angles. Here we can see that theta represents the geodetic latitude of the sphere. When we have theta equals 0, phi equals the 0 state. We're working with the North Pole. And when theta equals pi, psi is equal to the first state in the South Pole. And we have psi representing the longitudinal point of the South Pole. Looking at this example here where we have theta equals to 90 degrees or pi on 2 and psi equals to 0. Using our rule that we've developed from before, we get psi is equal to 1 on root 2 base state 0 plus 1 on root 2 base state 1. This gives us a point where the positive x-axis intersects the Bloch sphere, as we can see on the left-hand side here. Looking at this example here where we have theta and phi both equal to 45 degrees, using our existing rule, we get psi is equal to 0.92 base state 0 plus 0.27 plus 0.27i base state 1. This is represented on the left-hand side here. Another example now where theta is equal to 180 degrees and psi is equal to 90 degrees. Using our existing rule again, we get psi is equal to 0, 0 state plus I, 1 state. This gives us a point that is exactly on the south pole of the Bloch sphere. Looking at this last example where we have theta is equal to 45 degrees and psi is equal to 270 degrees, we have psi equals to 0.92 base state 0 plus negative 0.38i first state, which on the left hand side we can see how these angles are interpreted with the Bloch sphere. One thing with the Bloch sphere is when we have a position that's on the equator, this means that the probability is 50-50 of each state. The closer a position is to one of the poles, means there's a greater likelihood of finding this qubit in the basis state at that pole. To summarize, the Bloch sphere is used to visualize quantum bits in quantum computing.